Okay, then let us start. So our plan for today is to try to talk about Koch's rings, which is also called the homogeneous coordinate ring of a variety. So it was not previewed in the plan, but I thought it is a good topic, which is quite logical here. So first of all, for those who followed the previous lecture, one proposition which is more or less obvious from the last lecture, but we will use it today, so I state it. So suppose that our fan is complete. Then last time we studied the sheaves OXD, and for them we have an exact formula for all the global sections. So first of all, for OX, there are no global sections. The only global sections are constants. The global sections of OX sigma, this is only constants. Then the second, we constructed in this case PD. So in our case, PD is a polytope. Polytope for any Tn invariant Weyl divisor D. On X sigma. And the third is that the global sections are finite dimensional. X sigma O X sigma D has a finite dimension as a vector space. Over C for any Weyl divisor D. So all this stuff follows from the formula which we proved last time, is the formula which expresses the global sections of OXD. So we've had a polytope. What is PD here? PD. So PD, take D, which is expressed in prime divisors as the sum of A row, D row. Okay? So A row are integers and D row are our prime divisors, which correspond to the rays of the fan. In this case, last time we explained this formula. So PD is the set of all M such that this scalar product, the pairing product of M and the ray generators mu rho is greater or equal than minus A rho for all rho rays of sigma. So this is the definition of the polytope PD for a Weyl divisor D, and as it is stated here, it is given by a finite set of inequalities, so it can be unbounded. What is written here is that for a complete fan, this object is always bounded. So this is in fact the only thing which we need to prove here, that this is bounded. If we prove that this is bounded, then the global sections is in fact labeled by the lattice points of M which are in the polytope, and this number will be finite. Or maybe I should write down the formula. So this is a PD, and the formula which we have is that we assume that this formula is known, that the global sections of OXD is in fact the direct sum for all M in PD, the one-dimensional space generated by the character chi M. So this is from the previous lecture, and this is what we need for the complete fans. Also this stuff. Why this is only C? So to prove A, this is quite easy. If we have a monomial which for this case D equals 0, so all the A here are 0. So we have that M is such that for any ray M U rho is greater or equal than minus 0, which is 0. But if this is true for a complete fan, then there is an integer combination with positive coefficients of U rho, which equals 0. And so we obtain that M equals 0. Is it clear? It is just a geometric fact. If we have a complete fan, such that the U rho go in all the directions, not in one subspace. There is no there is no half space in which all the U rho belong. Then there is a positive integer combination of U rho which gives 0, and if these inequalities are held, then we write here the combination given 0, and we get that all these scalar products are 0 and M equals 0. So there is no M looking in all these sides simultaneously. Okay, this is the proof of A. And now if we want to prove B, we want to prove that this is bounded. If there is a PD is not bounded, then there are some points which go far away, then there exist points M1, etc., where the value of Mi tends to infinity, the module of Mi tends to infinity. And we can get a contradiction with these inequalities in the following way. If we consider the points Mi divided over the value of Mi, the module of Mi, these will be points on the unit sphere. Since we have infinitely many such points, then there will be a limit point. So this sequence has a limit point on the sphere. But for this limit point, when mi tends to when the modulo of mi tends to infinity, all these inequalities will become that this is greater or equal than 0. And so we will obtain that this limit point also equals 0. But this cannot be true since this point is on the sphere. Is it okay? I want to show that for a complete fan, the polytope PD is bounded. If it is not bounded, then we take a series of points which tends to infinity. We take its limit point, and we say that for any, if this value, we can define it by m this limit point. If m u rho is negative, then we take the absolute value of this bigger, such that a rho divided by this value is less than this epsilon. Okay, so then change I, and we obtain that for the limit point m u rho greater or equal than 0 for all raised rho. And since the fan is complete, this gives us a contradiction. So the consequence of this is that m equals 0, but m is on the sphere. So we it has to look no, not 1. I mean, we can always I can explain this in the other way. If our fan is complete and our vector m is non-zero, the u rho are in the dual space, but nevertheless, so there is always some u rho which goes in the opposite direction. So this is u rho, and this scalar product will be greater than 0. So the vectors u rho are given in the beginning, so their absolute values are known. Okay. So we showed that that PD is bounded for the complete fans, and then the space of global sections will also be finite dimensional, because the space of global sections is exactly when we take this polytope and we take all the lattice points which are in this polytope. Last time we had different pictures, for example PD like this, and then there were lattice points yeah. Okay. And now I want to pass to Cox rings. So in the book of Cox, they are not called Cox rings. I suppose it is because he's the author of this notion. And it is not very good to name by yourself. So in some sense, today's lecture will follow not only the book, but also the original paper by Cox, which dates by 93. It is on archive. I think if you want to get the main idea, you should better read this paper. And if you want to check carefully all the details of the proofs, you should follow the book of Cox. I think that today we will explain the main idea, but not the proof in detail. Probably I'll try to give the proof in detail next time. So, for any toric variety, we are going to discuss the following objects. First of all, the Cox ring of X. So this is the homogeneous coordinate ring. This is a ring with some grading, which I will write it in 5 minutes. So I just say, first of all, this is the Cox ring of X, which is some graded ring. And in this ring, we will have the irrelevant ideal. Also, we are going to discuss the quotient construction. It is very close to this. We take a very big affine space, some affine space Cn. Then we throw out some union of coordinate hyperplanes. What is a coordinate hyperplane? Is a hyperplane where I say this, and this coordinate are equal to 0. I throw out some pieces, and then I quotient by some quasi-torus. So this is a product, this is an abelian group, which is a product of an algebraic torus by some abelian group. Okay?
Can you repeat?
A quasi-torus is an abelian group which is some torus, some C star power something, multiplied by some finite abelian group. So any abelian algebraic group can be expressed in this way. Its connected component is an algebraic torus, and also there is a finite group which expresses the group of connected components. I'm not going to prove this in detail, but I will write something to explain this.
Also, are we removing all the coordinate hyperplanes from the Cn? Are we removing, because at first it was like Cn minus
Some coordinate hyperplanes, not everything.
Okay. Not all the coordinate.
Not all of them. We will throw out a piece of codimension, usually at least 2. Okay. And also, maybe next time we will discuss ideals in the Cox ring and some varieties in the toric variety. Okay, so first of all, what is S? We assume that our toric variety is as usually constructed with the fan sigma. So sigma of 1 are the rays of our fan, and for each ray I take a variable. So x rho is a variable. So we have this set of variables which are labeled by the rays of our fan. Okay?
Also, in the first definition you said that it's a Cox ring of X, also some irrelevant ideal. I mean,
So this is our plan for today and also for the next time.
Okay, I mean, what do you mean by irrelevant idea?
I'm going to define all this. So this is just the motivation part. Even you are not obliged to write it down in your textbook.
Okay.
This is just a motivation. We will discuss this, and this.
Okay.
So first of all, what is the Cox ring? X row is a variable. Each variable for each ray. Then, I assume that sigma 1 spans n r. Okay? It means that our toric variety has no torus factors. We can omit this condition, but later. At the beginning, let us start with a toric variety without torus factors. Okay, and we just define as our Cox ring. It will be on just the polynomial ring in these variables x row. Each variable for each ray. Okay, maybe we need some example. The most basic example, we take Pn. What are the rays? We have n plus 1 rays. So each one has a variable. So we obtain C x0, x1, etc., xn. This is just the ring. I forgot to say that in this ring, each monomial, if we write a monomial which is the product of x row power a row, it is in fact a divisor. Divisor, which is the sum of a row d row. And if we go in the other direction, if we take any effective divisor is a divisor such that all the coefficients are non-negative, then for an effective divisor we can write a monomial. So this is our ring. And next, if we say that it is a homogeneous coordinate ring, we need to introduce a grading. Homogeneous, it should be with respect to some grading. No, we are going to grade with the class group. So let us recall that for each divisor, we have its class in the class group. So we had an exact sequence. Recall M, which stands for all the characters chi M. Then we've had all the Weyl divisors. The T invariant. Then the class group of X sigma, and then this is exact. We've had it 3 lectures ago. And we can say that the product of A of X row power A row and the product X row power d row have the same degree if and only if and only if they the corresponding devices have the same representative in the class group, which by exactness means that they differ by the divisor of a character. Okay? So if two elements coincide here, then their difference goes to 0, and then it is in the image of this map. So we say that we name these two elements the same if and only if there exists some monomial m, some element from the lattice, such that a row equals mu row. U row is the primitive vector on the ray, plus b row for all row. Is it okay? Just we want to grade our ring by the class group.
So the image of M will be the whole class group.
No, the image of M here will be all the principal divisors. All the divisors of a character chi M. What is the divisor of a character chi M? The divisor of chi M is given as follows. We take the evaluation of chi M along each d row. So this will be the sum m u row. This is the order of vanishing multiplied by d row. So this is the divisor of a character, and we showed that this sequence is exact. It means that if two elements, this one, the corresponding divisor, and this one, if they go to the same element in the class group, then their difference goes to 0.
Yes.
And then it is in the image of this map. Exact means that the image of this is the kernel of this.
Yes.
So the image of this, it means it has such form. Mm-hmm. So for some m, the difference can be expressed by scalar products of m with your row. Mm-hmm. Okay. Wonderful. So I raised this. I want to say that this is a well-defined grading of our ring S by the monoid, which corresponds to the positive part of the class group. The divisors can be effective such that all the coefficients are non-negative, and other ones. So in fact, we obtain only the divisors which are effective, because we take only variables in positive degrees, in non-negative degrees. So we the non-zero components of S correspond to effective divisors. We say that let S lambda be the direct sum for all the divisors such that the degree of xd equals lambda. Did I define xd? X power d means that if we decompose d in prime divisors, then I take the corresponding variables in the corresponding degrees. This is x power d. So this is the sum of c times x power d, and it is clear that to define a gradient, we need to mention that S lambda times S beta forms part of S lambda plus beta. Okay, just if the degrees equals elements alpha and beta from the class group, then if we sum up two divisors, the degree will sum up.
Will it be a proper containment or?
It depends. I don't want to say anything at this step, because the next statement which I want to say is that in fact all these S alpha are the global sections of this form. Maybe I erase the next blackboard. So our proposition, and then maybe after this proposition I will give some examples. Proposition. First of all, if we take some alpha, which is the class of a divisor D, then we can write down a map phi D, which goes from S alpha to H0 of X O X D in the following way. We take S alpha I wanted to write an exact formula. Okay, first I state that this is an isomorphism, and also I say that if we have two classes, alpha and beta, alpha is a class of D, and beta is the class of the divisor E, then if we take the product here as alpha tensored by S beta, it can be mapped to H. So first of all, here we map to S alpha plus beta, this map. And also we can map this to H0 of OXD, tensored by H0 of OXE, and also it can be mapped to H0 of this sum. So this can be mapped to H0 of XD plus E. So this and also this arrow. This is commutative. And every monomial of S alpha arises in this way. So how can we prove this? How can we prove this? The proof, it uses our polynomial PD. Our polynomial PD. We know that H0 of XOD is labeled by the m's which belong to this polynomial. So if we take m from PD, we can write the monomial xd plus the divisor of m, the divisor of chi m. Okay? This is well defined, since how can it be expressed using the variables? It is the product x row, a variable power something, power m u row, which stands for this divisor, and u row which comes from the d, plus, no, it was denoted by, okay, plus this coordinate of the, it was a row, okay? And what is PD? It is the set of m such that all these integers are non-negative. So if we take m from PD, then we take the variable in some non-negative power. So this is well defined. And in the other direction, if we have a collection of powers here which are non-negative integers, then these then if we write this, it will be non-negative, so the corresponding point m will be in the polytope. So this is indeed a bijection. If we take S lambda, S alpha, then it is the same as the global sections of OXD. And clearly, if we take two polytopes, one for if we take PD and PE, then we sum up these inequalities and the product will induce a bijection. So the product is well defined. If we take two elements here, and for this we can sum up the inequalities which were satisfied for the initial monomial. Okay, so if we take, if m satisfied m u row greater or equal than minus a row, and m u row greater or equal than minus b row, then we sum up these two objects and we say that no, not sum up. So we've had this sum which is non-negative, and this sum is non-negative. So no, this was m1 and m2. So one from this one and one from this one, and now we have m1 plus m2 u row greater or equal than minus a row minus b row. This stands for the sum of two divisors, and this stands for the product of the corresponding monomials. And so I have explained this commutative diagram. We have the isomorphism that each S alpha is in fact the global sections of the corresponding sheaf, and if we take a product of two graded components, then it corresponds to another sheaf which is the sum of divisors, which corresponds to the sum of the corresponding divisors. And one more consequence is that I said that at the moment our fan is complete. So if our fan is complete, then PD is bounded, and each S alpha is finite dimensional. Corollary. X complete all S alpha finite dimensional. Since they are labeled by the same polytope PD. Okay, any questions? Then I can give some examples. The most basic example here is the projective space. For the projective space Pn, what is our gradient? In fact, our gradient is by class group. What is the class group of Pn? So we have polynomials in n+1 variables, and effective divisors stand for z plus, and this is indeed the gradient by the degree of by the total degree. What is alpha? If we have an effective divisor, we say that so if two functions differ by the divisor of a character, then they're the same. Yes. So for us, if we have a divisor, it maps to the class group. We take only its degree, the sum of these. So what are our divisors? D0, D1, etc., Dn. Okay? So if we have a positive sum of AI, Di in the class group, so all these divisors are linearly equivalent. So two linearly equivalent divisors, they differ by the divisor of a character chi m. So this is linearly equivalent to A0 plus, etc., plus An, D, anyone, D0. And so,
is it clear that these divisors are linearly equivalent?
On Pn? Yes, because if we take two coordinates and we take their ratio, it is well defined on the torus. So it is a monomial, Ti, Tj minus 1.
Okay.
How did you prove that the class group of Pn is Z? You just showed that any two divisors are linearly equivalent. So we have the divisors corresponding to hyperplanes, something equals 0. And the ratio of the corresponding functions, it is well defined on the torus function. It is rational on Pn, but it is regular on the torus. So it is a monomial. And so these two divisors have the same representative in the class group. So it works like this, and the degree of some x0 power something, etc., is just the sum of the a0, etc., an. The next example is the weighted projective space. So, the weighted we also checked that the class group of the weighted projective space is also Z. But now, what do we have? X is P, Q0, etc., Qn. So recall that in the lattice N, we took the same vectors, but we subdivided the primitive vectors on the edges. The fan was the same as the fan for Pn, but the lattice was somehow subdivided. What is the Cox ring? The ring itself is the same. This is C of x0, etc., xn, but we have another gradient. Our gradient is the degree of xi equals qi. You see, so it is not exactly the same as for Pn. And so gradient by z. And the third example is the product of two projective spaces. This is also a very useful example, Pn times Pm. In this case, the class group is Z square. Okay? And what are our polynomials? We have n plus 1 divisors here and n plus 1 divisors here. So we have polynomial ring in two sets of variables, x0, etc., xn, and then y0, etc., ym. And we have the b degree. B degree. So it will be degree in x, degree in y. So this will be also a polynomial ring, but with another gradient. Okay. So now I think I will mention the order on the monomials, and then I will define the irrelevant ideal. Okay? I erase this. So, how do we define order on monomials? We say that, suppose that xd and xe are from S, then xd is said to be less than xe, if and only if we can change E by some linearly equivalent divisor, there exists monomal xf in S such that the degree of xe equals the degree of xf, and such that the monomial itself xd divides xf and xd is not equal to xf. This is the definition, and it is necessary to define what are the minimal elements and to explain why this is a monoid. So if X is complete, then this order is transitive, antisymmetric, and multiplicative. It means that if we have some xd less than xe, then xd plus f is less than xe plus f. Okay, it is more or less obvious. The only difficult part is why is it antisymmetric? So can we have at the same time xd less than xe and also xe less than xd? So if xd less than xe and xe less than xd, then it means that we can there exists some f such that xd divides xf. So the divisor f minus d is effective, and f minus d is equivalent to e minus d. So e minus d is effective, but at the same time d minus e is effective. So since our variety is complete, it can be held only if this is a zero divisor. So we don't have the globally defined regular functions, and we have E equals D. Okay, and the only constants, so the gradient S0 in our case for complete varieties, S0 equals only C, only constants. But you see that it is true for Pn. the only constants in the polynomial algebra are constant. So if we say that the gradient is by the degree, the elements of degree 0 are indeed the constants. Okay.
Можно вопрос?
Да.
Нам тут от Е только степень нужна, правильно?
Да.
А D, ну, как бы... А D важно, что это индивизор, да, а не класс. То есть если мы E заменим на эквивалентный ему, то ничего не изменится. Если D заменим, то может поменяться, да?
У D коэффициенты не отрицательны. У D коэффициенты не отрицательны, у F коэффициенты не отрицательны, и у них есть неравенство. Коэффициенты F больше либо равны коэффициентов D.
Не, мне просто как бы интересует, что эта штука, ну как бы этот порядок, он не спускается на группу классов, да?
So, in fact, this means that the difference F minus D has, if we decompose it using prime divisors, its coefficients are positive. And if we have the reverse, then for D minus F, its decomposition into prime divisors has positive coefficients. So it means that if we have an effective divisor, then we have a well-defined function. And in the reverse side, it also works. So, in fact, this is, so on the class group, we have a submonoid of effective divisors. If we sum up two effective divisors, we get an effective divisor.
I didn't understand the proof of antisymmetry. I understood that xd divides x by x, but after that,
So we replace E by another monomial which has the same degree,
yes.
and we obtain that the difference E minus D is effective.
Why?
Because so we say that okay, F minus D is effective. Do you agree? So F minus D is effective, and in the other direction, okay, we can find F prime such that F prime minus E is effective. Okay, this has the same degree as E, and this has the same degree as D.
Yes.
So if we sum up them, then we obtain an effective divisor of degree 0. The degree of a divisor is just the number of integers.
Yes.
So these two degrees coincide. Okay? By this condition, we replaced E with the divisor F of the same degree.
Yes.
So these degrees are equal, and these degrees are equal. So we have two effective divisors. We sum up them,
Okay.
and we obtain that they both were 0. Two collections of non-negative integers which give us a 0.
Yes, so it has to be 0 divided.
Yeah. Okay, till the moment we used only the rays of our fan. We didn't use the structure of the fan. It is quite strange. If we want to construct something interesting which would be an invariant of our toric variety, we need to use some more information. And now I'm going to define this. The relevant ideal. What is this? We can take, if we take a cone sigma in our fan, we can take the product of all the variables which do not enter in sigma. So the sigma head will be the divisor this will be the divisor, the sum of d rho, where rho is not an array of sigma. Okay, and the corresponding monomial x sigma hat, it will be the product of these variables, product for rho not in sigma, x rho. And now b, which depends on the fan, is the ideal generated by all x sigma hat. So b x sigma hat for all sigma in sigma. Clearly, we can take only maximal cones in our fan. Maybe I should give an example. The main example for today and the next lecture is the example of the projective space. The projective space Pn. For each cone sigma, for each maximal cone sigma, we take all the variables which do not participate. So for this cone, we take this variable. For this cone, it will be this. And for this, it will be this. So B will be the ideal generated by x0, x1, x2 in the polynomials x0, x1, x2. So the key idea of the quotient construction is that if we consider the vanishing ZZ, the vanishing of this ideal for Pn and for X. I mean, in this case, we can say that it is in the affine space of dimension n plus 1. So we have n plus 1 coordinates. What is the vanishing of this ideal? x0 is 0, x1 equals 0, and x2 equals 0 for Pn. For Pn, this is only 0 point. And how do we construct Pn? We take Cn plus 1, we throw out 0, and then we quotient by the torus, by one-dimensional torus, by homotheties. So Cn plus 1 without 0 by C star. This is the projective space. Do you agree? And now maybe we need another example. What is the irrelevant ideal for the product of two projective spaces? So what is Pn times Pm? What is our B? It is generated by xi, yj. Okay? So the maximal cone in the product of these fans is just the product of maximal cones in the fans for this one and for this one. So we take the remaining divisors, one is in the first component and one is in the second. And we take the corresponding monomial. So this ideal in C xi yj. Okay, what is the vanishing set? If we take the vanishing set of B, in fact, it is easy to see that if all x, y, y, j are 0, then either all xi are 0 or all yj are 0. Okay? So it is the union of 0 cross p m plus pn cross 0. And what does the quotient construction say? We didn't prove it yet, but we will explain it later. It says that if we take Cn plus 1 cross Cm plus 1 and we throw out this, not plus but union, 0 times Pm union Pn times 0. And then we quotient it by, what is our class group? Our class group is Z2. So we quotient it by C star square. So we should obtain our product of two projective spaces. This will be the quotient construction. What next? I think I will try to explain something. About the group which acts. So the statement, the accurate statement is as first we need to define the group and then I will say what is the exact statement about the quotient construction. So this is our example. We take the product of two complex spaces. We throw out some, no, not Pm, this is Cn plus 1. I'm sorry. This is Cn plus 1. And this is Cn plus 1. And this is Cn plus 1. And this is Cn plus 1. So we throw out some coordinate subspaces. And then we quotient by the torus. Okay. Our class group is Z2.
Просто там вместе звездочки двойка должна быть, да?
Да, спасибо. Что-то я уже совсем... Yeah. Okay. So, what did we explain? We constructed the ring S. We introduced a grading by the class group on it. And also we said what is the irrelevant ideal. And we discussed more or less what is the vanishing set of the irrelevant ideal.
Important thing. Is this irrelevant ideal graded? I think we need to prove this to get action of torus on.
Yeah. I think I can, if you want this, we can switch a little bit. I can say why is this a toric variety? Why is what a toric variety stands for? Stands for C power, the degree of the Weyl group, without the vanishing set of the irrelevant ideal. Okay? So I write Z power sigma of 1 just to mean the space labeled by devices. Okay? Sigma of 1 is the rays of our fan, and also C power sigma of 1 is just our new construction. We say that, suppose we have a fan, so we have a list of all maximal sigmas in our fan. And also we know our irrelevant ideal. Now, what is this? It has basis E rho, where rho stand for the devices, stand for sigma 1. And what is for our variety X? We've had U rho, the primitive vectors on the edges. So suppose that this complex space has E rho as a basis, linearly independent vectors. So this is just a new basis, a basis in this new space. We just formally constructed. And we say that a cone, so we say that E rho 1, etc. belong to a cone sigma T tiled in this fan. In this space, we are going to construct a fan sigma tiled. If and only if, just formally, if the corresponding U rho 1, etc. Belong to a cone in sigma. Okay? Just formally. If some vectors were generating cones in the fan sigma, we say that their preimages in this space will be in a cone. So what properties should we check? That if we intersect two cones, then their intersection will also be a cone. But this is true because if two cones intersect in sigma, their intersection is a cone here. So we list the U's which generate this cone, and they generate a cone in this space. What is important is that In fact, this fan is, if we construct this fan, it defines the variety C power this without the zeros of the irrelevance ideal. So we need to think why this is true. This is not very deep. This just stands for the fact that what are the irrelevance ideal? What is so recall that we have the orbit cone correspondence. So if some cone is not presented here, so first we complete this stuff, use the orbit cone correspondence, and say that if we throw out something, it was because it was in the zero set of the irrelevance ideal. So, for example, if we have Pn cross Pm, what do we have? We have Cn plus M plus 2, and what do we have as cones? The maximal cones will be generated by M, I write n plus 1 plus m plus 1. N vectors from here and m vectors from here. N vectors from here, and then from here. So why didn't we? So what did we throw out? We throw out all the xi, yj equal to 0. So we explained that we threw out all the points of this form and all the points of this form. And it agrees with the fact that we do not have cones which have all the n plus 1 vectors from here. So if there were the cone which has n plus 1 vectors from here, it will correspond to a point which has all the coordinates equal to 0, and we throw out all these points. And if so we don't have a cone which contains all these basis vectors because we threw out all the points which have all the coordinates equal to 0 here. So maybe it is not very exact right now, but I want to, if we take all the cones generated by these basis vectors, so this is the basis, and we have only part of the cones generated by these basis vectors. If we take all the cones, all the possible cones generated by these basis vectors, then we will have more points. Due to orbit cone correspondence, each cone stands for an orbit. What is an orbit for the complex space? Some coordinates equal 0 and some of them are non-zero. Do you remember? For Cn we did it by hand. And so if some cone is not listed, this is exactly because the ideal B vanishes on the point which has zeros on the prescribed points. I can repeat what happens here once more. What can be cones if we have just...
То есть я правильно понимаю, что мы выкинули две орбиты, эти орбиты означают какие-то...
На самом деле не две.
Две?
An orbit is some coordinates are 0 and some are definitely not 0. So this stands for 2 power n plus 1 orbit.
Выкинули как два замыкания.
Да, два замыкания орбиты выкинули.
И это вызвало выкидывание кучи конусов.
Да. Остались только те, которые приходят из сигма.
Это ровно вот то. Вот те конусы.
Да. So if you want to prove this very accurately, then we need to define what is a primitive set. So a primitive set is, one moment, a primitive set is the set of indices such that if we throw out any one of them, then it will be in some sigma. And this set itself is not in any sigma. So we say, do you want this accurately?
Нет, понять пытаюсь.
It takes some time to understand this in detail.
Нет, ну понятно.
А я для того пример нарисовала. If you want to understand, I think it is... If you want to understand, the example should work. So we say that C in sigma 1 is called a primitive collection. So this will be the set of labels which stand for some subspace which we throw out. It is a primitive collection if, first of all, C is not in one cone for all sigma and sigma. And the second is that for every proper C prime and sigma, there exists a cone in our initial fan such that C prime now is in some sigma 1. For our P n times P m, the primitive sets are all the I and J. Yeah or no? No. For Pn times Pm, we take okay, that's a good question. What is the primitive sets for Pm times Pn? No, we just take n plus 1 coordinates on one hand, and this will be all the U0, etc., UN, and any subset here, any subset of cardinality at most m vectors here. Does it work? No, it doesn't work. We just take this one and we take v0, etc., vm.
Можно
Да.
еще проще? Для PN.
Для Pn.
Там
Да.
Получается, это просто все.
Да. For Pn, this is the set of all u0, etc., un. Because this is not in one cone, and if we throw out any one, it will be in one cone. And for this one, it is similar. If we so first of all, on one of the hands we should have all the vectors, otherwise they're already in one cone. So it has this on one hand. If it has something else on the other component, if we throw out only this vector, it will not be in some sigma. Is it okay? No? First of all, so let us discuss what are primitive collections for Pn times Pm. Да. The answer is that the only two primitive collections is this one and this one. So this corresponds for the primitive vectors on the edges of this Pn, and this corresponds to all the primitive vectors on the edges of the second Pn. Why is it so? First of all, at one of the sides, it should contain all the vectors. Because if not, then this collection is already in the product of sigma for this one and sigma for this one. So if it has all the u's and some vi, can it happen? If no, it is the statement that the only possibility is to take this union to satisfy both conditions. It's forbidden to add something else. If you add something else, it will not be a primitive collection no more. We need these both properties to be satisfied. Okay? So if we add some vi, B will not be satisfied, because for every proper subset, I take a proper subset without vi, and I have all the vectors for Pn which are not in any cone. So this is forbidden, either this set or this set. The only two possibilities. Now our statement is that the zero set of this irrelevant ideal is in fact labeled by the primitive collections. So the irrelevant ideal, if all the monomials vanish, then the coordinates which do not vanish, they will satisfy the properties of this stuff. If we take the maximal collection here, I mean, if some coordinates vanish and some not, if we make zero those ones which were not zero, it will also be in the zero set. So let us take the maximal coordinate subspaces which are here. What are the maximal coordinate subspaces of zeros of VB? can it contain variables which are in one cone? Definitely not, because if all the yeah, it will not be zero if all the rays of some sigma will be non-zero. So if we mark those ones which are non-zero, they will form a primitive collection. No, those ones which are zero, they will be primitive collection. Okay, so I have explained that the primitive collections exactly stand for the zeros of the irrelevance ideal.
It's like irreducible components, right?
Yeah, exactly. They are for they label the irreducible components of the zero set. And now in this fan we need to throw out all the coordinate hyperplanes which stand for the primitive collections. And exactly what remains, it will be the cones which come from the initial sigma. So, in some sense, we have constructed this toric variety. So, its torus is just the C star power sigma of 1. This is the toric variety with the lattice and with the torus. And this X is the toric variety with the lattice N, with the fan sigma, and the map from this space to this space, which maps E rho to U rho. It is согласовано. It is okay with the fans. So we said that a map between two toric varieties is called toric if each cone from the first variety is mapped to the cone of the second variety. And if the
cones map to the cones.
yeah, the cones map to the cones, and if the lattice is mapped to the lattice. In this case, the both conditions are held, so this map is indeed toric. The next step is to say what is the torus, no, what is the kernel of the tori which are from here to here. And I will say that it will be exactly so the group, the quasi-torus to quotient will be the homomorphisms from the class group to C star. This will be our quasi-torus. And our aim will be to quotient this without this stuff by this quasi-torus to obtain the initial toric variety. This is very much similar to how we construct the projective space here by quotienting over C star. But in the cases when the class group is not free, when it has torsion, our quasi-torus will indeed be a quasi-torus. It will have more than one component. Okay, I think I will stop today at this point. If this is interesting, I will continue about the quotient construction next time.
То есть мы хотим доказать, что действительно получится то же самое количество.
Да. Мы хотим доказать, что если мы выкидываем из большого афинного пространства наборчик маленьких афинных подпространств и факторизуем по какому-то квазитору, мы получаем то торическое многообразие, с которого мы начинали. Это называется как бы фактор конструкции. Okay, thank you. If you have some questions, write them in Telegram.